Hi, it's Professor Gressley, your favorite lab partner, and let's get started on the simple harmonic motion 1 lab. All right, I'm going to shake myself down, and here we go. So this lab we're going to be using 3 things. We have our instructions file, we have our pivot interactive, and then tucked back here I have my lab skeleton. So if you want, go ahead and pause me now and get those 3 things ready to go. All right, this lab we are going to repeat some of the skills that we learned in the Pendulum Lab series. And so this lab video is going to be a little bit shorter than the Pendulum one because you already know how to do a lot of these things. So I want to start off by introducing you to this Pivot Interactive with the, what they're calling it, a linear oscillator. The reason they're doing that is because it moves up and down in a straight line. Well, we're assuming it does. And also because it oscillates, which just means moves up and down. So, all right. So what we have here is, let me press this. Okay. Is a whole bunch of springs that we can choose from for this lab, and they're labeled A through G. We're actually going to label them by their spring constant. More on that in a little bit. Then we've got a whole bunch of masses that we can hang from the end of the spring. So here's the spring in the picture. And then here's the mass hanging from the spring, and they put a little red X in the middle of the mass so kindly to help us track that thing. And then amplitude, they have 5 different amplitudes that you can choose from. And that is how far you are going to actually stretch the spring before you let go. So let me check out a medium amplitude, a medium mass, and a medium spring, and load. Okay, and let's just see what happens. So here we have, here's what's happening zoomed out, and then here's the little picture zoom in there. Our tools that we have for this, we have a ruler tool. We can use this to measure the amplitude, how far they stretch the spring before we start. We've got a timer, so we can measure things like the period of the spring. So I'm just going to press play. Let's watch what happens together. So she pulls it down till it touches the screw, and then she lets it go. And we watch it move up and down, up and down, up and down, up and down. Oh, how exciting. Okay. So let's go back to the beginning. Okay, she's holding on to it, and I'm using my arrow key to just kind of fast forward until she lets go. Okay, so at that point where she lets go, right there, she's still kind of touching it. This distance here where the X is from the 0, I line the 0 up with the X at the very beginning. So this distance here is the amplitude, and it's amplitude number 3. So amplitude number 3 looks like it's 1, 2, 3 and a quarter centimeters. So I would say 3.25 centimeters. That's how big amplitude 3 is. You're going to want to measure all the amplitudes. And amplitude 3 for this spring is the same as amplitude 3 for the other springs. So if this is 3.25 centimeters, it's 3.25 centimeters for all the other spring mass combinations too. So that's good to know. Okay, and then she lets it go. And it goes up and down, right? So the first thing I need to tell you is what is a period for this. And a period for this is where it starts low and goes up and comes back down. So that's 1 period. If I count how many periods this thing did before she let go, let me rewind. Let's see how many it did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this one did 12 periods after she let go. Now, when we're taking data, we do not want to use that very first period because there might, we might not actually get where she let go perfectly and stuff. So what I'm going to do is forward until I get it to its lowest place next. Let's see, that's about as low as it's going to go, and then I'm going to set my timer to 0. And then, just like in the Pendulum Lab where we timed how long for 5 periods, that's what I want you to do for this, because some of these spring mass combos are really fast. So I'm going to press play, and we'll go for 5 periods. 1, 2, 3, 4, and then I'm going to just slow down for the 5. Okay, that's about the lowest, 5. So it took 4.6000 seconds to do 5 periods. So that would be my data point for this one setup with Spring DE Mass 500. So I would do that. Okay, so like the pendulum lab, you're going to repeat that measurement another time. Okay, so I got 4.6000 seconds this time. I'm going to repeat it again and see if I get the same exact time there. And by repeating again, I mean you could reset this to 0 again too. Okay, so that's getting the average time for 5 periods. And I've shown you all the different things. So yeah, okay, well, let's just get started then, starting the lab, and I'll keep this open so we can just look at it as we go. Oh, all right, so your goal is to measure the spring constant. Oh, this part here, I need to remove that from, because you know what, we're actually not doing this. Boom, there, objectives are shorter, always a good thing. You're going to run a controlled experiment. That first objective was if we were doing the lab in person. Okay, so first, we're going to brainstorm in the lab records. What are 3 things that you can change about this system? And you know what? I'm just going to tell you right now, it's really super lame when we use a pivot interactive because the 3 things you can change are spring, mass, and amplitude. Specifically, instead of spring, we're actually going to change something called the spring constant. And spring constant is how stiff the spring is. So make myself bigger and just talk a little bit about that. So springs are various stiffnesses, and I only have one spring with me for the video, but this is like a slinky, and you can see it's not very stiff. It's pretty easy to stretch, right? And so we measure the stiffness of a spring by something called a spring constant. This here would have a low spring constant because it's very easy to stretch. Other springs, like springs, let's say in your car's hydraulics, are harder to stretch, and so they would have a high spring constant. I like to call it the stiffness of this spring also, but officially it's called spring constant, and it's represented by the letter K. All right, so the stiffness of this spring is called spring constant, represented by the letter K. Awesome. All right, so that's one of the things that we're going to change here. Each one of these springs, A through G, has a different stiffness or spring constant. The other thing we can change is how much mass is hanging on the end, and then we can change how far we pull the spring before we let go. So go ahead and pause and fill in the brainstorm with those 3 things now. Fantastic. Okay, next we're going to fill in our experimental design templates. So I've filled in the research question for you already. The dependent variable in all of these is going to be the period of the spring in seconds. So you can fill out period for all 3 templates. Go ahead and pause and fill that out now. Okay, and then the independent variable is going to be whatever you brainstorm. So say the first thing you brainstormed was the spring constant, and those are measured in newtons per meter. Maybe the second thing that you brainstormed was the mass of the mass on the end of the spring, and that's going to be measured kilograms. And my cat wants to be part of the video as usual. And then the other thing, amplitude, oops, oh, thank you, Microsoft, and it's measured in meters. So go ahead right now and fill out your independent variables. Hi. Okay. Next, controls. Control is going to be what you're not changing. So in this experimental design template, I am changing the spring constant, which means I shouldn't change the mass on the end, and I shouldn't change the amplitude. Okay, but that's not all, right? We have to fill out what mass and what amplitude we're going to pick. I have some bad news. If, like, for example, for spring D, do you see how some of the masses are grayed out? Because spring D either doesn't give good data for lower masses or would break if we put a heavy mass on it. So you need to check out these masses and click on a few of them to see which ones give you the most springs, right? So like if I click on 500 grams, you'll notice that springs C and E are no longer available. So that's a really bad control because I would only be able to test F, G, D, B, and A. That's just 5 springs, and you know I like to test 6. So click around on the masses and pick one in the middle that has at least 6 springs that you can test. Same with amplitude. I think all 5 amplitude 5 looks like it's a bad idea. Oh, for that. Oh my goodness. But anyhow, pick an amplitude in the middle that you know you can test for all your springs, okay? So for this amplitude, just a note, for right now, let's just say you picked amplitude 2, but write yourself a big note, measure this, and put it in here later, okay? Because definitely for sure, I'm going to highlight this. You want to go into the Pivot Interactive and find out actually, what is amplitude 2? How far is it? And then write how far it is here. Okay, because you want the value, not like 2. You want, remember how in amplitude 3 I measured it was 3.25 centimeters? So if I picked amplitude 3, I would write 3.25 centimeters here. Okay. Oops, it's in caps. I need to make sure my centimeters are not in the wrong case. There we go. Okay, but for sure, okay, pick an amplitude, and put that in there later. So actually a really good idea right now is to fill out your control variables and put in the amplitude. And FYI, here are the spring values. So when you're controlling for spring constant, here are the values. So you should put in the newtons per meter of the spring that you're going to use as your control in to the controls also. So for example, for this one, I'm going to have to control for spring constant and say I used spring C, and then I want to put in the value. That's very important. Okay, so now pause, put in those controls. All right, testable hypothesis. Again, it's very simple. I don't mind repeating it. This is just saying that we are hypothesizing that spring constant affects the period. That's it, okay? And then in prediction, we say our prediction, I'm going to say like lower spring constants will have longer periods. That's just my guess. So you can put in your guess there. Remember, you can be wrong with the predictions. That is just fine. So go ahead right now and fill out your hypotheses and predictions for each one of your templates. All right, we are ready to design our experiment. Here are the questions. I ask them in every time we do an experiment like this. What are the correct units for your first IV? I had spring constant for mine, so newtons per meter are the correct units for spring constant. For amplitude and mass on the end, you're going to use kilograms, meters, or seconds, depending on which one's most appropriate. Those are the correct answers in the correct physics units. So if you'll notice, the Pivot Interactive is not using the units that you should use in the lab. So you will have to convert those numbers when you put them in your Excel data table. So don't put in 100 grams. You want to put in 0.1 kilograms when you use that. All right. So go ahead and answer 1, 2, 3, 4, and 5. I don't know why I have a 6. Sorry, if you have a 6 on yours, just ignore that. So go ahead and answer the rest of the design your experiment questions now. All right, now you're going to do your experiment. So you're going to test. Let's say you're testing spring constant and you picked 300 grams and amplitude 2 as your controls. So you pick a spring, press load, and then, find the period for 5 springs. Oh my goodness. Find the time for 5 periods and then do it again. And then you find the time for 1 period. Okay, so let me write this down because what I just said, it's really hard to follow words. But basically, when you're doing the data, right, I'm just going to type it over here. And I'm going to make my, my text a different color and bold so you can see as I'm typing, is you want to measure the time for 5 periods twice, okay? So that's repeats, how many repeats? You're going to do 2 repeats, so that's the twice. Then average, whoops. Then find the average time for 5 periods, right? So you're going to average your 2 numbers, and then you divide by 5. Then divide by 5 to find average time for 1 period. This is just like what you did for the pendulum lab. So what you want to do is go ahead now and do your whole experiment and put your data tables, get them ready to go. It's going to be a long pause. Go ahead and do that now. Fantastic. Now get those Excel data tables. Okay, these should have just your IV and your DV. Okay, so one column will be, for example, average time for 1 period and spring constant, right? That'll be one of your data tables. Another data table will have average time for 1 period and mass. The other one will have average time for 1 period and amplitude. I do know there's only 5 amplitudes instead of 6. I know, but I won't get rid of your points. Don't worry. Okay, so make sure those Excel data tables are imported into this file. Make sure you have units. Make sure you're in kilograms and meters and newtons per meter. Go ahead and do that now. All right, now we're ready to draw some conclusions with the data. Now, we're not graphing the data yet. We are just looking at numbers. I know, how tempting is it to graph the data? We're visual creatures. Graphs are amazing things. You can just look at a graph and know what's going on. That's really amazing, and you start to count on that. And here's the deal. You also have to have the skill of being able to look at columns of numbers and see what's happening, and that's what we're practicing here. So, was your first IV positively, negatively, or not correlated? Remember to use our words. Don't use the words like directly, indirectly. Nope, nope, nope. These are what you're going to conclude. It's either positively correlated, negatively correlated, or not correlated. Then, how does your data support your answer? So you want to use numbers in this. You want to quote from your data table. As my spring constant went from 5 to 30, my period went from 2 to 0.5. So I had a negative correlation because one got big and the other got small. You see how I use numbers in there. So use your numbers. And then confidence. Remember, confidence is always a percentage. Do all the numbers go up and down together, or are there some glitches in there? Tell me in your confidence. If you see some pairs of numbers that did the opposite, your confidence might be down, okay? Now, your confidence is matching your conclusion. So if you said they were positively correlated, then you're like, I am 95% confident they are positively correlated. You want to match. I've seen a few people say they're positively correlated and then say they're 10% confident it's negatively correlated here, which is very confusing. Okay, so you are going to answer these questions about your conclusions and confidence levels for all 3 sets of data. Remember, not graphing, just looking at the numbers. Go ahead and do it now. All right, we're close to the end because the next step is you are just going to make that graph now. Make that graph. So I'm glad we get to make the graph. It's so much easier to see the correlation with a graph. But we're only looking at dots. Don't put any best fit things in there, okay? We are just looking at dots. And what you're going to do is make the graphs with the dots. So go ahead and pause, make those graphs with the dots and put them in there. Don't forget titles and axes, labels, and all those beautiful things. Do it now. All right, you got those graphs in. Now we're going to make conclusions with the graphs. So we're going to write a conclusion for each graph. Remember, in the conclusion, don't just say, for graph number 1, they are positive. I want you to tell me what is in graph number 1. Is graph number 1 your mass graph? Then say mass is positively correlated with period. Then for reasoning, you're going to talk about the slopes between pairs of numbers. The slope is going up as, you know, between each pair of numbers. Or you can tell me the dots are moving up and to the right in a pattern like this. Or the dots are moving down and to the right. That would be a negative correlation. Or the dots are moving up and down. That's a no correlation. So you can use those types of terms. Tell me your conclusions and your confidence levels. Don't forget your percentages for the graphs. You're going to write those 3 conclusions here, 3 confidence levels here. So don't forget to separate them. And then finally, the last thing for the lab is roll it all into one general conclusion. I think my face is blocking. I'll move my face. How is this, all of it correlated? You know, is it all positive? Or you know what I mean. Just read this. I don't want to confuse you. So you're going to write one sentence overall conclusion there. And that is it for simple harmonic motion number 1.